The Magnus Effect, exploring the force behind spinning objects. This is the title of discussion in this lecture. A similar video was posted yesterday in the same channel, in the same YouTube channel, where Cristiano Ronaldo, that football player, means about his expertise in the field of soccer game, that was discussed. And there also the Magnus Effect was discussed, but not in detail. Here today this video I am going to discuss the same thing, that is Magnus Effect, in detail. So actually this topic, Magnus Effect, you would find in the subject of fluid dynamics or fluid mechanics. Fluid mechanics means that is the summation of fluid dynamics as well as fluid statics, means hydrostatics. Okay, so mainly fluid dynamics is there, and in the course of fluid dynamics you would find this topic Magnus Effect. Okay, actually the analysis of this Magnus Effect is very difficult if you want to use the full Navier-Stokes equation for the solution. Again, if you want to, if you use Euler's equation of motion to solve the same, then also it will be very difficult. The knowledge of computational fluid dynamics would be required to solve such problems. But here we are going to discuss only the principle behind this force. Magnus Effect is nothing but a force. Okay, so for example, in which case this is required, means analysis of this is required in which case? If there is a spinning object, means the object is spinning about its own axis. The object is rotating about its own axis, as well as there is a relative motion between the object and the fluid surrounding it. Relative motion is necessary, not necessary that the object must move. Okay, that is not necessary. If relative motion between the object and the surrounding fluid is present, then, and also one more thing is there, that spinning of the object must exist. Then in that case, you would find the effect of Magnus Force, and that is known as Magnus Effect. Okay, so for example, say we are talking about an object which has a translatory motion. Okay, which has a translatory motion, and the fluid surrounding it is not moving, it is stationary. Okay, just for example, suppose that object is spinning around its own axis. So what happens? Say the object is rotating in the clockwise direction like this. Okay, the object is rotating in the clockwise direction, and the object is moving from left to right. This is left, this is right. Okay, the object is moving from left to right. So what happens? If you observe carefully, then you can see that the upper part of the object, say for example the object is moving in a horizontal direction from left to right. Then if you consider the upper part of the object, then you can see that translatory motion is from left to right, and the upper portion is rotating this way. That means the direction of the upper part, the motion, the spinning motion, okay, the direction of the spinning motion of the upper part and the direction of the translatory motion are same. So in that case, what would happen? The fluid surrounding the upper part will have acceleration. Velocity will increase of that fluid. And just opposite to that, means if you consider the lower part of that object, okay, you can consider the object to be cylindrical. For simplicity, you can consider that way. Okay, and if you now consider the lower part of the same object, then you can see that lower part motion is clockwise, that means it is rotating this way. So if you consider the lower part, that means it is moving in the opposite direction of the translatory motion of the object. That means there will be retardation of the fluid velocity. Okay, see, that means fluid velocity decreases in the opposite direction of the same object. Okay, so on one side there is an increase in velocity of the fluid, and on the opposite side there is a decrease of the velocity of fluid. So if you now use the concept of Bernoulli's theorem, then you know that if velocity increases, therefore pressure decreases, and when velocity decreases, pressure increases. So on the upper part, the fluid velocity increases. That means there is a decrease in pressure on the upper part. And just on the opposite side of the cylinder, means we are taking the example of a cylindrical object, okay? That's why I am saying cylindrical. And on the lower part, the pressure increases because velocity of the fluid decreases. So at the lower part, pressure is more than at the upper part. And that's why there is a net force should act. There is a net force should act in the upward direction, vertically upward direction, if the translatory motion of the object is horizontal, in that case, vertically upward direction. This vertically upward force, the force which is acting in the vertically upward direction, this force is known as the Magnus Force. The effect is known as Magnus Effect and the corresponding force is known as Magnus Force. And here the direction of the force should be both perpendicular to the axis of the spinning axis or the axis of rotation of the object, and as well as perpendicular to the direction of the translatory motion. It is the Magnus Force must be perpendicular to both the direction of the translatory motion as well as the axis of rotation. Okay, so that will be the direction of the Magnus Force. By using right hand rule, you can easily determine the direction of the Magnus Force by using right hand rule. Okay, so we were discussing about a problem where the object was having a translatory motion and the fluid surrounding it was stationary. Again, if this be the case, say the object does not have any translatory motion, but the fluid surrounding it is moving. Okay, then in that case also same effect would be observed. Again, if both are moving, both the object and the surrounding fluid is moving, in that case also you would get the effect of Magnus Force. Okay, but spinning must be present. If spinning remains absent, if the object is not rotating, in that case there will be no effect of Magnus Force. Magnus Force can't be observed in case of non-rotating object, means object which is not spinning. And the same effect, if you have got expertise in this field of aerodynamics or fluid dynamics, and say you are a baseball player or you are a football player, in that case, if you can precisely control the force on the object, that means here in this case, in case of soccer, it is football. Okay, so if you can precisely control all these things, then you can change the trajectory of the ball according to your will. Okay, according to your will, and in that case the the players of the opponent team won't be able to predict the path followed by the ball, and that is the advantage. And to take just that advantage, you can use the concept of Magnus Force in case of games such as baseball or football. So yesterday a video was posted where the free kick of Cristiano Ronaldo was discussed. You can watch that video also, but there you would not get this Magnus Effect in detail. Anyway, in case of engineering applications, you would find this effect. In aerospace engineering, near the wing or on the wing, this effect can be used to generate additional lift. In case of naval ships also, to reduce the fuel consumption, this effect can be used. Okay, the effect of Magnus Force. Again, in the design of turbines, means rotating objects. Okay, this effect should be considered. Okay, and there is a mathematical formula for this. Force is equal to a constant k into area into angular speed into density of the fluid, okay, into velocity of the translatory motion. This is a simplified formula. Only for simple cases this formula can be used. Here the area is, you can see on the screen this formula. Here the area is nothing but the projected area of the object. Omega is the angular speed of spinning, okay, and velocity means here v means velocity, which is nothing but the translatory motion, okay, which represents translatory motion, magnitude of the translatory motion, and rho is density of the fluid, and k is a constant of proportionality which depends upon the surface texture of the object, which depends upon the shape of the object, like that. Okay, but this is a simplified formula. Okay, in all the cases you cannot use this formula. Anyway, so this was all about the Magnus effect behind spinning objects. It means this is the science behind the spinning objects. No, not like that. This is not the science behind the spinning objects. This is the science behind unpredictable trajectories followed by the spinning objects due to the effect of Magnus force. Okay, anyway, so this was all about today's topic, the Magnus effect. Okay, so this is the end of this video. Thank you for watching this video.